Hello, I'm 이.광호 from Zro2 University. The subject I'll be presenting is evaluating effectiveness of dust byproduct treatment with scrubber to mitigate explosion risk in zirconium oxide ALD process. The paper is the Journal of Hazardous Materials in 2020. Authors are 이.광호, 송두근, 리제찬, and 정승호. Organization is Department of Environmental Engineering, Zro2 University. Keywords are atomic layer decomposition process, dust byproduct, explosion hazard, industrial waste, semiconductor industrial. This is introduction. Atomic layer deposition is a method that allows of deposition of highly controlled thin film on various substrates on the vapor phase. The technique has been widely used in a large variety of applications such as fabrication of semiconductor logic and memory device. Despite the extensive use of ALD process in semiconductors and related industrial, ALD is not always efficient, and a significant amount of unreacted precursor materials can flow through the production chambers and post-processing piping. The unreacted chemicals might lead to unexpected reaction occurring inside the downstream piping, resulting in the generation of significant amount of byproduct. According to a survey conducted by Samtech, more than 17 incidents have occurred from during 5 years in semiconductor and related industrial, and among the 17, 14 incidents occurred at downstream of tool. In addition, the byproducts may be harmful to human health. For example, 21 employees at the semiconductor manufacturing facilities in the Republic of Korea were recently afflicted with headache and had to be hospitalized due to the leakage of gas and particulate byproducts and non-reacting chemicals from a pipe connected to a vacuum pump that broke due to an increase in the pipe temperature via heating jacket. In this regard, this study evaluated byproducts of an ALD process using TDCA and ozone to produce desirable zirconium oxide film with two different scrubber systems. To evaluate the effectiveness of the treatment of dust byproduct with different scrubber to mitigate explosion risk in the zirconium oxide ALD process, untreated byproduct generated in the same ALD facility was also characterized, and its characteristics were compared with those of two treated byproducts with dry scrubber and burner scrubber. The result of this study would help not only suggest more effective method to treat byproducts of ALD processes that present explosion risk, but also develop better safety controls for ALD manufacturing process in semiconductor industry. Material and method. 3 byproduct samples were collected during the maintenance at the full-scale ALD zirconium oxide manufacturing facility that is depicted. The byproduct generated in the ALD process is handled by using primary scrubber and main scrubber. Primary scrubber is used to treat particularly the dust byproducts generated from the zirconium oxide ALD process. Main scrubber is a kind of house exhaust system into which exhaust discharge from the other process involved in the whole semiconductor manufacturing factory. In this study, the byproduct before and after entering the primary scrubber presented at the pictures. The 3 samples were collected and used for all experiments. Case 1, byproducts generated from zirconium oxide ALD process with a dry scrubber treatment. Case 2, byproduct generated from zirconium oxide ALD process with a burn wet scrubber treatment. And third, byproduct generated from zirconium oxide ALD process without any treatment. This is the analysis method. And the byproduct generation in zirconium oxide ALD process, although most volatile byproduct can effectively be treated by heating the flow line, less volatile byproduct can deposit inside pipes through the post-production facility. The deposited solid materials may contain mixture of substance that can explode upon exposure to water or oxygen. Hence, the byproducts deposited in the pipeline incur the considerable explosion risk. Therefore, they need to be properly treated in order to reduce the explosion risk as part of a process safety strategy. In following subsections, materials characteristics and thus explosion characteristics of the byproducts with and without the scrubber treatment. The byproduct particles were between 0.4 and 40 micrometer with mean particle size of 4.217 micrometer for case 1 and case 2 and case 3. The reason why the particles treated with the dry scrubber were smaller than those treated with the burn wet scrubber was likely due to sintering of the particle occurring during combustion. Although most volatile byproducts can effectively be treated by heating the flow line, less volatile byproducts can be deposited inside the pipe through the post-production facilities. EDS element analysis demonstrated that 4 elements are present in the byproduct as summarized in Table 2. Note that the absolute composition of the sample were not valid as the EDS was not calibrated. However, the EDS result can be compared from sample to sample. Comparison of the EDS result between case 2 and case 3 indicated that carbon, nitrogen, and oxygen are leaving the byproduct upon combustion of the sample. Dry scrubber treatment had little effect on the elemental composition of the byproducts. Represent TGA profile for the 3 byproduct sample. The sample of case 1 and 3 exhibited similar TGA profile, but the sample of case 2 showed a different TGA pattern. The TGA result clearly shows that the byproduct treated by burn wet scrubber is more thermally stable than the byproduct treated with the dry scrubber and the non-treated byproduct. In other words, the burn wet scrubber treatment of the dust byproduct generated from zirconium oxide ALD makes it more thermally stable. The composition and oxidation of the byproduct sample was also studied by heating the sample in pure air. Shows that an exothermic reaction was initiated at 88 Celsius degrees and gradually liberated heat under the air atmosphere. A major broad exothermic event started at 413 Celsius degrees and finished right before the highest measurement temperature. Integrating the area under the major peak gave a reaction enthalpy of 4.816 kJ per gram. FTIR analysis revealed a peak in the region between 3,300 and 3,600 per centimeter, which can be attributed to oxide and hydrogen bonds, and it thus indicative of the presence of moisture in the byproduct. The peak between 1,240 to 1,400 per centimeter represent the carbon and hydrogen bonds in alkanes, and those at 1500 to 1740 per centimeter represent the nitrogen and hydrogen bonds in amines, which have a high risk of explosion. In the sample of case 1 and 3, the peaks for amine and alkyne are strong, but they are weaker in the case 2 sample. This was likely because explosive organic residue remaining in the byproduct had been combusted by the Burnwell scrubber treatment. Thus, the fire risk would be lower with the use of Burnwell scrubber because of the removal of amine and alkyne base material. The pressure data as a function of time obtained from the dust explosion device for the 3 byproduct sample are presented. The peak pressure of the byproduct treated with a dry scrubber and the untreated byproduct was bounded to be 7.6 and 7.0 bar, with a similar maximum rate of pressure rise of about 270 bar per second. When the Burnwell scrubber was used for the treatment of the byproducts, the peak pressure was bound to be 0.9 bar with a maximum rate of pressure rise of 60.4 bar per second. The maximum rate of pressure rise for the byproduct sample of case 2 was 50 times lower than that for the byproduct sample of case 1 and 3. Given that the maximum rate of pressure increased after ignition of the dust byproduct indicates the explosion robustness. This clearly indicates that the Burnwell scrubber treatment decreased the robustness of explosion caused by the byproducts generated from the zirconium oxide AID process. The minimum ignition energy is the minimum energy input that is necessary to initiate explosion. Any flammable materials, including dust, must have their own MIES. Therefore, the MIES of the byproduct sample of case 1 and 2 were measured. The 3 byproduct samples were not ignited at 1000 millijoule. This means that the byproduct samples are difficult to ignite at typical electrostatic discharge energy. As a result, the key result of this study can be summarized as follows. First, the dry scrubber treatment led to a smaller average particle size of the byproduct than the Burnwell scrubber treatment. Note that smaller particles can lead to a higher risk of dust explosion. Second, the Burnwell scrubber treatment affected the elemental composition of the byproduct. Third, the Burnwell scrubber treatment resulted in making the byproduct somewhat stable. Fourth, the Burnwell scrubbing of the byproduct decreased surface functionalities that are associated with explosion. Finally, the robustness of dust explosion caused by the byproduct was 7 times decreased dry the Burnwell scrubber treatment. The Burnwell scrubber is a more effective treatment method than dry scrubber to mitigate the risk of dust explosion potentially caused by the dust byproduct generated from AID process. Thank you for listening my presentation.